All right. Hello, everyone. My name is Hugh McKee. I'm a developer advocate at Lightbend. And the topic in this talk is clustered event sourcing with CQRS implemented with some example codes in Akka and Java. So at the end of the talk, I'm going to give you a bunch of links to 6 different projects that kind of progressively build up through some, if you're new to Akka, some interesting things about Akka. And I'll be telling you a little bit more about Akka during the talk. But ultimately up to a couple of projects that have a working implementation where you can run it on your laptop in multiple command windows, or run it on some containers in your favorite cloud system, and set up an Akka cluster where you're running multiple nodes. So there were some talks earlier this week that were pretty good about event sourcing and CQRS. How many guys are familiar with this? Is this something new? Wow, okay, pretty good. Anybody using it in production or anything? Awesome, all right. So I'm not going to spend a lot of time on some of the mechanics of it, just kind of a very brief introduction to event sourcing and CQRS, because what I really want to do is show you some code that I've got as an example for doing event sourcing and doing what's called the query side. So, but in this diagram, what I'm showing is this is my version of a diagram I saw in some Microsoft documentation. And by the way, if you're looking for some decent documentation on event sourcing and CQRS, Microsoft has a ton of it, which really surprised me. And there's a lot of really good stuff, and they've been doing it for quite a while, so it's not new to them. We have a lot of, at Lightbend, we have some tools that use it, and we have some good documentation, but there's multiple sources. Well, anyways, what I'm trying to show in this diagram is that with event sourcing and CQRS, is kind of there is this separation or segregation, and it kind of starts at the service level. The way to kind of think about a service is that a service is either getting commands, do something, asking the service to do something, or it's getting requests to perform some kind of query, retrieve some information. So that's what's happening here. On the left, you've got a client that's sending in either commands or requests for queries. If it's a command is an intent to do something. I want to deposit something into my bank account. I want to add this item to my order. I want to remove this item from my order. Things like that. But it's a request. So these commands come in. There's very specific requests, and they go into the service, and the service basically validates the request. So say, for example, we're doing a withdrawal from a bank account. If the account has insufficient funds for that withdrawal, you would reject that request. However, if the account has sufficient funds, then the withdrawal is allowed to be performed. So that what results in that is events. Withdrawal. Added to withdrawal. It's a past tense. An event is something that's happened in the past. It's a historical fact. With event sourcing, and it's also a mutable fact. So what we're capturing with event sourcing is just events. So part of the rationale for this is that there's a lot of reasons why I like event sourcing and CQRS, but one of the big ones is performance, in that this is a very, very fast way to capture data. That you have, say, a service is very busy, it's getting lots and lots of commands at a very high rate, and you're not going to have high contention at the database level, which is typically where we start to run into contention and things slow down, because all we're doing is insert very simple into a very simple data structure. It's just like a key value data structure. Cassandra is often used for the event store, or Kafka, things like that. Very, very fast. So you can capture these events very, very quickly. So say you get a spike in traffic, this service can just scream. It has a much higher threshold for handling load before it runs into a problem. Now, it does come you might consider it a cost, but I think I like to think of it more optimistically as an advantage in that now I have a service that can capture these events very, very quickly, but that's called the write side. So we're just writing events into this event log. On what's called the read side, you have another database, another data store where you're persisting data that's optimized for queries. So this is what I'm showing here in the diagram on the left, where these events are being communicated to the read side. And I picked the word communicated because they're not necessarily being pushed, and I'll get into that in a little bit. But in any case, the query side, the read side, is your favorite database. So it could very well be a relational database. So it could be Cassandra on the write side for events, and maybe MySQL or Postgres for queries. Now, but there is this kind of eventual consistency gap between the two, right? Because say we have two different databases, so we don't have a transaction that spans these two things, so we have one transaction where events are going into the event log. That's done, and now we got to guarantee that these events are going to be handled by the read side. So there are ways to do that where you get at least once messaging delivery guarantee, for example. And I'll be showing you that in a bit in the code. But the other thing, though, is that this is kind of addressing the trade-offs that we've been dealing with for a long time. This is another advantage I really like about event sourcing and CQRS, is like with traditional databases, we're always kind of balancing, tuning the database for writes and reads. You add you add indexes to optimize reads, but it comes at a cost at writes. So you can't add too many indexes before the writes slow down. So you got to be very conservative about your indexes, things like that. Here it's separated it. It's like the query database is probably denormalized and is very optimized for queries. That's it. And the only thing we have to worry about is events going into it, right? Otherwise, it's read only. The only write operations are events being, streaming in from the write side to the read side. But then that read side is, again, it's very optimized for the queries that the service provides, right? So a service has a well-defined set of queries that it's providing. Because another thing with microservices as well is that there's no backdoor way into the data. If you're really doing microservices the way it's intended to be done, the only way to get to the data is through the service API. No backdoors. If you're on a team that owns that microservice, you know what the schema looks like, but nobody else knows what that schema looks like. That's the goal. Doesn't always happen, but that's the goal. So when you can do those kinds of things, now you have this option where you have very optimal data stores for your queries and very optimal data stores for your events. So just as a quick example, there's still a concept of like my bank account, what's my current balance. There's still a concept of my order, what's the current state of my order. But it's really kind of this aggregation of all the events. So in a bank account, which is fairly simple, is deposit withdrawal, and then the sum of all those deposits and withdrawals is the current balance of my account. So the account is derivable from the aggregation of all the events that occurred before that. Now, as an optimization, there's a mechanism called Snapshots, where occasionally you can save the state of the entity, because what happens is that when you want to recover the state of the entity, you don't have to, like if you have a bank account with a very long history, you could have thousands of events. You don't have to spin through all those events to recover its state. So the idea is that occasionally you snapshot the state of the entity so that the recovery would be, give me the last snapshot and any events that have to happen after that last snapshot. And now you've recovered your entity state, like the bank account state or the order state. The other thing that I think is really interesting, especially now that we're getting into this day and age of we want data, we want to analyze data, we want to feed data into our analytics systems, that's getting big, that with event logs, you're not throwing away data anymore. So, for example, say you're building an order, and you're adding an item to the order, you update the quantity of the order, maybe you add, change the quantity from 1 to 5 and then change the quantity back to 3, maybe you remove some items. In a traditional system, typically we would have just kept the end result. How many items are in the order, what are the counts, that kind of information. When you have an event log, you end up with all the history. And things like the term I've heard is negative data. So negative data, things like you removed an item. Well, typically that would just be some maybe update or delete that we would do in a traditional database kind of application. Here, you got all the history. Well, the data scientists are getting hungrier and hungrier for that kind of data. This is a kind of another advantage for this kind of an approach. So what's clustered event sourcing in CQRS? Well, this is kind of an Akka thing. How many of you guys are familiar with Akka? Pretty good. Okay. Akka is why I work at Lightbend. I came across Akka in a Coursera class, and it was love at first sight. I loved the program. I loved the challenge of programming. And building Akka is an actor system. So you're writing actors. And it's a really different way. It's not hard. It's just different way of architecting and implementing a system. And I just fell in love with it. It was just, once I kind of wrapped my head around it, which wasn't that hard, and got it into it, it was like, I can't believe I can do these things. And things like this, where you can write an application or a service that's not constrained to a single JVM. You can have a collection of JVMs running in a cluster. And each JVM could be running in a different container or in a different server, those types of things. It runs over the network, but it behaves from a programming standpoint as a single big machine. And that's what an Akka cluster is. So the example I'm showing here is that I've got 4 nodes, 4 JVMs running on 4 different machines or 4 different containers that are talking to each other over the network, and I'm creating actors in that environment. And these actors are being distributed across the cluster. So in the case of event sourcing in CQRS, the main player, the main actors are what are called entity actors. So every entity that's currently getting commands has an actor representing that entity. So, and it's somewhere in the cluster. And there's no complicated message routing to these actors. As a developer, we don't have to get involved in that. It's being taken care of for us by Akka itself. It's really easy to set up. And we're just kind of focused on, well, I got to write the code for the entity. I don't want to worry about all this plumbing of having to do this distribution of actors and everything like that. That's being taken care of for me. And you, if you were doing it. So the idea is that commands are coming in for entities right now, and there's actors representing those entities right now. And when those actors come to life, they're sitting there in memory. They're not holding threads. They typically have a very small memory footprint, usually in the order of hundreds or maybe a K or so of bytes. It's not a large footprint. And when those actors stop getting commands, they get bored and shut themselves down, to free up resources. So the idea is that it almost kind of acts like there's only the actors that are in memory that are in play. Once they're not in play anymore, they go away. So more commands come in, more actors get created. But the cool thing here, and this is one of the big payoffs, is that say one of the nodes goes down, right? We had a whole bunch of actors on there. In fact, typically JVMs scale to the level of millions of actors per JVM. Okay? So say we lose a node, and we had lots of actors on that node. Well, there's the philosophy in Akka of let it crash. I don't care, because these actors will be restarted as needed on other nodes in the cluster. And the sample projects that I'm giving you have these things built into it, right? So just as a quick aside, I know a lot of us are doing microservices, or microservices has been hot for a few years now, and I'm working with some customers right now that are doing it. I've talked to a lot of other people that are doing it, and excuse me, it seems like there's a variety of implementations. And the point I'm trying to make here is that you're not just splitting up the code, but often the goal is to split up the data. Because the big objective with this new philosophy for building systems is loose coupling, independence. Each service is independent from the other one. And you get that real independence when you have independence of not only the code, but of the data itself. So that's what I'm trying to show here, that on the left-hand column, I'm starting out with a monolith, big hunk of code, big database. A very common pattern is you break up the code, you start having microservices, but you haven't broken up the database. This is really, really common because it's so hard it's easy to break up the code, relatively easy, but then you start talking to your database guys, and I used to work at a company that had data architects and things like that, and they go, oh no, we're not breaking up this database. You can forget that. That's not happening. And that's fine. At least you can break up the code. But if you can push it and you get to the point where the service owns the schema, then you're starting to get in business, right? Now you have independence. Your team is responsible for your schema. Nobody else sees your schema. All they see of your service is your API. That's the goal. That's loose coupling. Take it a step further in the fourth column. You move from, say, a single database under a microservice to event sourcing in CQRS. And there's a big advantages with that. I'm doing whole talks on that. Other people do whole talks on the advantages of this approach. One advantage that I really like is in this last column, the fifth column, where I'm trying to show multiple read-side databases. So say, for example, some of your queries are best served from SQL, but other queries would be best served from Elasticsearch. Things like that. This is doable in this kind of an approach. I don't know if you've ever tried to synchronize, say, your primary database with a secondary database. I have, and it was hell, because we would get millions and millions and millions of things replicated, but we would miss a few, and we were a bunch of jerks, right? We had a bug that we had to fix. It was horrible. This is why I like this kind of an architecture. There's a way for at least once message delivery. So what I'm going to leave you with are 6 projects, 6 relatively simple projects that are in GitHub. Sorry, I got a cold, and I'm trying not to cough too much. That you can download. You can put them on your PC, just do Maven compile, and then I've documented in the README how you can run it, and you can run, say, multiple nodes on your PC. Like I'll show you where I got 4 command windows, and I started 4 nodes, and these things talk to each other. So just a little bit about actors, and I'll show you some code in a minute. But I'm going to kind of build up from kind of stepping away from just a basic actor to actors that are what I call cluster aware, where the actors, the one sample project I have has an actor that knows that it has a counterpart in other nodes in the cluster, and it uses that fact so they can send message to each other across the cluster. So that's what I'm trying to show here in this diagram. Say one cluster aware actor is sending messages to the other 3 in a 4-node cluster. Same thing with this one. The third cluster aware actor can send messages to the other one. So let me show you that project. So this is the Java code for an actor. It's pretty straightforward. Here, all I'm doing is extending a base class, this abstract logging actor. And there's really only one method that I have to implement. And it's this one, create receive. So what I'm defining here is the way that this actor will handle incoming messages. Now, Akka is responsible for getting messages to me, and it's things like one actor sends a message to another actor, and it's over the network. Akka serializes the message, which is just a Java object, sends it over the wire, gets it on the other side, deserializes it, and then sends that message to the actor. We don't have to write any of that code. That's all done. All we're working on is defining how we receive and handle incoming messages. So this actor is quite simple, and that it's defined to handle 3 incoming types of messages. One's called tick. It's just a string. String is, I'm kind of cheating here. Typically, it's an object of some kind. And there's no limitations on the object other than it has to be serializable. That's it. Because it has to be serialized to go over the wire. Another message is ping, and another message is pong. The tick is actually, I'm just going to show you real quick here because I don't have a lot of time, that I'm using a scheduler. So this actor is scheduled to send itself a message every 10 seconds, basically. So it's going to send itself this tick message every 10 seconds. So it's a way to kind of trigger itself to do something. So tick comes in. If the incoming message matches that string, then I'm going to invoke this tick method, which is down here. And this is where it gets the cluster aware, which isn't complicated. It's basically just saying, hey, cluster, first tell me what member am I in, right? What node am I on? Yeah, so it gets back this member. And then it loops through all the members in the cluster. So it's easy for me or you to say, get what does the cluster look like right now at this moment. So that's what's happening with cluster state.get members. And I just loop through those. And if the member is not me, not my node, and that member is up, members have state, so I'm checking the state. Is that other node up? Because it may not be up. It could be shutting down. It could be starting up, those types of things. And if it's up, then I'm going to call this other method called tick again, which in here, this is where I'm building a path to be able to send a message to another actor. So it's called a actor selection, and there's also actor references. And it's very much like a URL. It has a host, a port, and a path. So that's what I'm building here. I'm asking the member for its address in the first part, and I concatenate it with the path to myself. Because this actor is going to talk to an instance of itself on another machine. So in order to talk to it, it knows it's at the same path location on the other machine. It just needs to know what that other machine is. So that's why it's kind of concatenating its path with that host and port from the other machine. It's just building a string. It takes that string and converts it into a what's called this actor selection. And then it logs it out just for fun. And then this is where you send a message. Actor selection.tell. .tell is the method for sending a message. That's it. And in this case, the message is going, again, over the wire to another machine. It could be going to an actor on the same machine. It really depends on where that actor is at. But in this case, it's going to another actor on another machine. So it's sending out just a simple ping message. Well, that actor on the other machine is this code, right? So a ping is going to come in to this actor. We're going to go to the ping method down here. Ping is real simple. It just logs out who sent me this message. The method sender here returns me the URL, the actor reference of the sender. So a message is kind of like an envelope. There's the body of the message, which in this case is just the string ping, but it could be a much more complex object. But it also has who's this message from, who's this message to, the sender and the receiver. So in this case, I'm just logging out who sent me this ping, and then I'm responding back to that actor. I'm just saying, hey sender, I want to tell you pong, right? So the pong comes in, and again, it's the same thing. This instance of this actor on the other machine gets a pong, invoke the pong method, and the pong method just logs out, all right, I got a response back. So these are asynchronous messages going back and forth between these actors. When one actor does a tell, it doesn't wait for any kind of response. It just fires off the message, and then this actor continues to run. Now, sometime later, that message will arrive in this other actor. So you're dealing with asynchronous messages happening between all these different actors. This is one of the differences in dealing with actor systems, is the asynchronous nature. It's one of those things that's not hard, it's just different. Once you wrap your head around it, it gets pretty cool, I think. So that's it. That's kind of an introduction to a very simple actor that can run in a cluster. This is a single project that you can set up and run. I don't have enough time to run this one. I want to run the more interesting ones for you. So let me move on. So there's this concept of there are out of the box with Akka, there are other actors that they provide for us. So one of them is called, it's got kind of a pattern of actors or a group of actors called cluster singleton. And what this is that there are some situations where even though you have a cluster, you want to have one actor that's responsible for some task in the cluster at any one time. And you want to be guaranteed that there's one actor in the cluster. So you could write this yourself. It's not that hard. But it's such a common pattern that the Akka team decided they're going to provide it for us. So it's relatively simple to set up. But the idea is that you have this actor on the bottom here that, this cluster singleton actor on the bottom here that is, there's just one instance of the cluster. So again, let it crash. If we lose that node that cluster singleton's on, the cluster singleton will be started up on one of the other nodes remaining in the cluster. We don't have to write any code to do that. We don't have to write any code that knows where that actor is, because another actor that comes with cluster singleton is what's called a cluster singleton proxy actor. So if I have an actor, I have this cluster singleton aware actor, say that's yours and my actor that we wrote, and we want to send a message to the cluster singleton, we just send the message to it, the local proxy. So say, for example, in the third node, this cluster singleton wants to send a message to the actor wants to send a message to the singleton actor. It first sends it to its local proxy, which is fairly straightforward, and then the proxy is responsible for figuring out where the heck the singleton's at in the node. We don't have to write any code again to do that. This is kind of sure. Network partition that's a whole other thing. I'll probably have to talk later about it. Split brain and split brain resolution. Good question, but it's a whole other topic. But yeah, to answer your question real quick, the idea is that a network partition is that nodes are up, but some nodes can talk to each other. It's like, say we had a split right down the middle. The network broke, say, between two data centers. So two of the nodes on the left are in one data center, two of the nodes on the right are in another data center. The network breaks between those two data centers. All the nodes are up, but split brain resolution is that you call it split brain because your cluster is split, is that one side has to shut itself down and the other side has to decide it's going to stay up. That's the trick to it. There are ways that this is done and handled. So in that case, the cluster singleton would be resurrected on the winning side. So it's like, you have cluster aware actors, cluster singleton actors that enable things like, are enabled by things like cluster aware actors. Now that I'm going to step it up, now there's another pattern of actors called, out of the box that comes with Akka, called cluster sharding. And this is really important for what we want to do for event sourcing. So the idea here is that you've got a bunch of entity actors. Remember I said that in that first diagram you have entity actors that represent, say, the bank accounts or the orders and things like that, and they're distributed across the cluster. With cluster sharding, the idea is that when you want to send a message, like a command, to one of these actors, it's cluster sharding that handles the routing. So there's no form of session affinity that you have to worry about. A command could be sent in from any node in the cluster. And the idea is that you send the command to the local shard region actor, and that shard region actor has the intelligence collaborating with its own cluster singleton to know where that entity actor should be in the cluster and forwards the message to it. So again, that's all happening for us. We don't do it. It happens really, really fast. Akka is really optimized to do these kinds of things, and it has a very high scale. So I want to jump in and show you the real projects, the last two projects of the 6-project series. And all these projects that I set up start out with, I just call it a class runner, and it's got the main in it. So this is just kind of a sample of how do you start up an actor system in Java, and pretty straightforward. The real work is happening down here, where we're starting up an actor system on a certain port. So each actor system typically runs on its own port because that's what it's used to do network communication. But that's it. I mean, it's almost like the actor system's kind of like, you can think of it almost as a glorified thread pool in a way. I mean, it's got a lot more intelligence, but it's not super heavyweight. It comes up fast. It doesn't take a long time. It's just something that you start in a JVM. This next line of code is an example of, all right, I got an actor system. Now I want to start an instance of an actor. So the code is actorsystem.actorOf. I give it the class name, and then there's this props method. Props are kind of Akka's way of doing a new. And then this actor is alive on this node. All right? The more interesting stuff, though, happens starting down here, where I want to start up cluster sharding. Now, starting up cluster sharding is pretty simple. There's an API for it. Cluster sharding get start, and I need to pass it a couple of important things. So what is the actor that's going to be used for individual entities? So that's what I'm identifying here, this entity persistent actor. And I'm giving it the props so that Akka can create new instances of this actor when needed. The other one that's kind of important is this message extractor. So let me show you the code here for that real quick. So the message extractor, what it does is it's set up to handle or take a look at incoming messages and pull out the identifier. So in this example project, I'm simulating commands and query requests, messages coming in. So with this, these are just messages, and in this case, let's see, that's the shard ID. Let me show you this one. I'm just pulling the ID from that message. That's all I have to do here. I'm just returning a string that Akka is asking for, which is give me the ID of this entity. That's all it needs, and then it's going to use that to route messages to instances of entity actors distributed across the cluster. A lot of magic is happening in here in the implementation, but for us as developers, the implementation this is it. I mean, you just have to define a message extractor, and then cluster sharding's up. And what's going to happen is that we're going to, as needed, when commands are being sent in for specific IDs, actors are going to be created to handle those incoming messages. The other thing is that I've got these two additional actors. One's called the entity command actor, and another one's called an entity query actor. So let me show you this entity command actor. So the entity command actor is just another basic actor. It does something interesting here in that it actually has two different ways of handling messages. It's called switching behaviors, or kind of switching state in a way. It's kind of almost like a finite state machine, where this actor is either in a sending mode or in a receiving mode. Now, this is my invention, but when you're changing behavior, all you're doing is changing what methods will handle incoming messages. So, as an example, when I get a tick message in a sending mode, I handle it differently than when I get a tick message when I'm in a receiving mode. That's all I'm changing here. Very commonly used, though, once you start to get comfortable with actors. So in any case, what I'm using this actor for is to generate random commands, just to kind of simulate activity, because this is just a demo application. So this actor comes to life. It schedules a tick, so every interval it's going to fire off a command to a random entity, right? So the way that's done is in the tick method. So in the tick method, tick sending, there's this method called command, where I'm just creating a random entity ID from 1 to 100 and a random amount from negative 10,000 to 10,000. And I just use that. If it's less than 0, I make it a withdrawal. If it's more than 0, I make it a deposit, right? And then this command is then sent to the shard region. Remember the shard region, that it's kind of that proxy. I send the command to the shard region, and I'm done. This is my code, your code, we're done, right? The magic happens where this message will be routed to an instance of the entity actor for this ID because of the message extractor and the way we set up cluster sharding. Sorry. So the entity persistent actor is a little different. I'm extending a different base class, abstract persistent actor. And this guy has two methods that you need to override and implement. One is for recovery. So what happens is when an instance of an entity actor is instantiated, it needs to recover its state. And its state is derived from all the events that have been previously recorded in the event log. So that's what's happening here. Because this is defined as a persistence actor, this actor knows what its ID is, and the prior events for this ID are recovered and fed back into this actor. Now, I'm not using a snapshot here just for the sake of simplicity, but again, the snapshot could be fed in, and then all the events from the last snapshot. So it just recovers. It doesn't recover all of its history. It just recovers from the last snapshot forward. But this happens real quick when the actor is brought to life, because when the commands are coming into these entity actors, they'll shut themselves down. After that happens, then we settle down to business, and here we're just handling incoming messages like a deposit command, a withdrawal command, a query request, things like that. So if we look at deposit's fairly straightforward. What we're doing is, you can see the call to persist. This is where we trigger the action to save an event in the event log in Cassandra. In this case, this is set up to run with Cassandra, this project. This tag command method is one that takes a command and returns an event. So you can look at the code later, but basically we persist it, and then there's when the persist finishes, there's this method that's kind of a callback method, handle deposit. So in this case, I'm just looking at what comes back from the persist operation. If it's all good, then I update my state. I make the decrement or increment based on deposit withdrawal, and then I acknowledge back to the sender. All right, it's all good. I got your command. I did what you asked me to do. So I send an acknowledgement message back. So that goes back to the command actor. Okay, so that's it. That's kind of the plumbing that's happening, where we're just capturing commands are coming in. They're being validated and translated into events. The events are being stored, and the actor updates its state. Like, what's my current balance? Or what's the current state of my order? Or whatever your entity happens to be. And it also, there was another message here. I'm sorry. Let me show you. It's not a message. There's this idea of passivation, meaning that when the actor doesn't receive commands for, say, a certain period of time, like a minute or whatever, you can define it, this actor will shut itself down. So it's a little bit of code for doing that. All right, I want to show you the final project in the last few minutes of the time I have. So that was the right side. That's handling the events going in. This next project, a little bit more involved, not too much, but it's doing the read side. So what's happening here is that the events are going in, their transactions are done, and then somehow we need to get those events from the write side to the read side. So there's this concept of what you can think of it like as a read side processor. So what this read side processor is doing is, instead of the producer of events pushing those events to the consumer of events, this side, what's happening is these read side processors are pulling. And this is why things like Kafka uses offset-driven consumers. This is an offset-driven consumer. What this guy is doing is it goes to its last offset. What was the last event that it successfully transferred from the event log into the query side, and then processes all the events after that. That's the mechanics of what this actor is doing. And it's pulling. So the idea is that the write side could be up and running. We're capturing events, but say the read side's down. Maybe the database is down, or maybe the node that this read side processor was running on is down. So the write side's getting ahead. Events are accumulating, but it just keeps working. When the read side comes back up, its job is to catch up, right? So it's just using the offset-based approach to catch up. So don't have a lot of time to go into the code here, but the code's in this this actor. The real action is in this read side processor event tag actor, it's called. Now, the other thing is that the reason for the term tagging is a way to have more than one read side processor. So the idea is that when you're writing events, you're tagging them. And the tagging strategy is kind of based on like a shard ID. You take the identifier, you create a shard identifier from it, which is like grouping a bunch of different IDs within a certain tag range, so that you can have one read side processor per tag. So the way I've configured this code is I've got it set up for about 20 tags, right? What that means is I can have 20 read side processors running concurrently spread across the cluster. And for that is the reason is throughput. I want those read sides to be able to keep up. Now, the number of tags and the number of read side processors is really determined by you, by the designer of the services. Where, say that you don't anticipate high volumes on a particular service, so you don't need more than one read side processor. On the other hand, say you do have a high volumes, so you want to have the option of creating more read side processors. So that's kind of the strategy. So this class, it is definitely more to it, but it's still just a basic actor, and it really starts. It's an actor, but it's really not receiving messages. It's an actor that's kind of brought to life, and then it just goes to work. And with the way Akka Persistence query works is that the first thing I want to do is I want to create a table called the offset table or read progress table. This is a custom table that I created because where you store the offset is really determined by you. Optimally, you're storing the offset within the same transaction that you're updating the read side database. If you don't, you can. That's doable, but there's other complexities that you have to think about that I really can't go into here because of lack of time. I'm so sorry. There's so much to cover here. It's such an interesting area. But anyways, this is where the offsets are stored per tag. So really what I want to do is I want to get that offset. And this is where this query happens here. It's just a Cassandra query. And once I get that offset, then I want to read events by tag, starting at that offset. If I don't have an offset, I default to the no offset. If I do have an offset, I'll go to the offset. And then I'll read the events by tag, which the result here is that it creates an Akka stream. So the query is an Akka stream that never ends. So once we're set up and running, there's an Akka stream running in this actor that's just receiving, as events are being added to the event log, this guy's receiving them. If it's behind, it's receiving them from a query. If it's caught up, it's receiving them as they're being created. So let me just show you real quick running something here. So I'm going to go to the fifth project, which was creating entities. And I'm going to run 4 nodes. I've got these aliases defined that made it simpler for me, and they're in the README file, these aliases as well, to make it simple to kind of switch projects and start up actor systems. So I want to So I've got Atom loaded up, and you can see I'm already in one of these logs. So first off, there's one actor that's just sitting there looking for cluster events and logging them out. So that's what I'm showing here. So you can see that actor sees that there's 4 members in the cluster. The more interesting stuff, though, is that here are entity actors that are waking up. An entity actor sent a command. You can see it's for ID 71. And I'd already run this test, so there's some data in the database. So when ID 71 comes up, it's recovering those events to recover its current state, which in this case is its current balance. And then it handles the incoming command. But they're running on 4 different nodes. Like this is the first node. If I go to the 4th node, the same thing. I've got a bunch of actors running, and everything's cool. The system's up and running, but I'm running on 4 nodes. Now, I can go back here and say I kill the first node. All right? And the way you stop one of these things is you just hit enter. And all right, the first node is down. So don't have time to look in the log, but if you could look in the log and see what entity IDs were being handled by node 1, and now those entity IDs are being handled by somewhere in node 2, 3, or 4, right? Didn't write any code to do this, right? Again, that's the big thing. A lot of really cool stuff's happening here with not a lot of heavy lifting on our part as developers, right? We're aware of this going on, but it's happening. That we kind of have to be aware that we're running in a cluster and these types of things. But we're not doing a lot of heavy lifting to make this work. So the idea is, let me shut these guys down, or they just keep generating data. Let me go back to the slides and wrap up. So these are the projects. These are links to the 6 projects. All real simple. You can download them, may even compile. And then the README has instructions on how to run them and run them in, say, multiple nodes if you want to do that. It's progressive as well, that the first project starts out with something really simple. With just that cluster, I call it a cluster listener actor. The guy is logging out what nodes are in the cluster. And you can see that one. It's this very simple actor. Excuse me. The next project is going to cluster where. Sorry, I'm really losing my voice now. Add another actor, then cluster singleton, cluster sharding, persistence, and then persistence query. So the 6 projects that kind of build up on each other. All you can grab. The only requirement is you need Cassandra set up on your machine for the last 2. But you just kind of start a Cassandra, get the default Cassandra, run it, and go. And if you're interested, a while back I wrote a little booklet on Akka. It's a very gentle introduction if you're interested in learning a little bit more about Akka. And that's it. Sorry I'm run short on time, but we got about a minute and a half for questions. And thank you very much.